So then we have something called a lower hemisphere projection. So this is a visualization tool. Part of a big part of engineering, especially when dealing with data, right? But a big part of engineering is visualizations, coming up with clever visualizations. Because rarely in real life and solving real problems are you ever going to be approached with a problem that has a single solution like you do here in school, right? And we grade you to the 9th decimal place. Right? That's not real life, right? In real life, you have uncertainty on all your parameters, and you want to understand how that uncertainty affects the results. You know, there's a lot of things that sort of come into play, and so being good at coming up with clever visualizations can help you make decisions, right? And so that's what this lower hemisphere projection plot is a way to sort of cleverly visualize, compile a lot of information into one plot. And so the idea here is that if you had this lower hemisphere, and right at the center of this guy, there was a derrick or a drilling rig, right? And you drilled somewhere through this guy in an arbitrarily oriented deviation. The point at which it crossed out of this hemisphere corresponds with these iso lines on this contour. So this is actually what's called a conformal mapping. So I'm taking that and mapping it to this guy conformally, where, you know, this line corresponds with this line. This line corresponds with this line, and so on, right? And so the idea here is, if I had a well that was, maybe as I have it drawn here, that was arbitrarily deviated, say drilled directly east and deviated 30 degrees, right? So directly east and deviated 30 degrees, it would cross out right at that red line, and the way you would plot that point is right there, right? If you had a horizontal well that was drilled directly to the west, right, it would correspond to that point right there, right? Because this is 90 degrees here. So 90, 60, 30, vertical is down there. So a vertical well would just be right in the center of this guy. Okay. So if we use this this information as a visualization tool, basically we can sweep through the angles of all possible angles, right? Sweep through all possible angles in phi, and we can fill up this whole picture with information. Right? Now, of course, it has to be single value information in this case, right? A point, but we can do it, and we can come up with some clever visualizations, right? So let's look at a couple examples. So here's one where the color bar is delta P, right? So this is basically saying what the delta P must be for a stable wellbore. Now, I'd have to go look at the caption to recall what a stable wellbore was, but I'm sure it's based on some wellbore breakout criteria, right? But basically, the idea here is that, so the required delta P for wellbore stability. And so in this case, if you're drilling in, so everyone on this plot sort of represents a direction that you could drill, right? So if you're drilling sort of in this direction at highly deviated area, in highly deviated areas, then you're required to have this much delta P for wellbore stability, right? If you're drilling horizontally in this direction, then you're required to have this much delta P for wellbore stability. Okay? And so that's one example, but there's others you can come up with. So, for example, the required CO for breakout initiation, right? So this is using a Moore Coulomb failure model and solving for the required unconfined compressive strength according to that model, in which any breakouts would occur, right? And then under different faulting regimes, given different stress orientations, right? So the idea here is that, the cool colors represent, you can expect to have no breakouts even with lower strength rock in the cool colored areas. You can expect to have, basically, you're required to have a higher strength rock if you anticipate no breakouts. Now, to just simply say required CO for any breakouts is not that useful because, of course, if you have breakouts, it doesn't mean you have an unstable wellbore. Right? So it's not the most useful criterion. Of course, if you want to be extremely conservative and say, I don't want to have any breakouts at all, then you can use some information like this. But basically, these are just maps at which you can look at quickly and understand, so for example, if you just looked at this, one thing I can say is that if I'm drilling horizontally in the direction of SH max, I better watch my breakout, I better really watch my wellbore for stability issues. If I'm drilling horizontally in the direction of SH spin, I'm probably going to be okay. And so again, the way you create these is because you're plotting a single value, in this case the required CO, you basically have to go through, you have to go at every point, at every delta and phi, right? Because remember, this represents 360 degrees of delta and 0 to 90 degrees of phi, right? Every point on this map represents that. So at every delta and phi, you have to go through all of those equations and then make some decision about what you're going to plot at the end. And this is why it's so important to learn how to use a computer, because it's impossible to do this by hand, right? I mean, it's not impossible, but it would take you 2 years to do all of those computations by hand. If you can do them the beauty of a computer is if you can do them for 1 point on the computer, like you might do by hand, then all it takes is 2 for loops and you can do it for all of them, right? A for loop from 0 to 360 over phi, and a for loop nested in a for loop 0 to 90 over delta. And then a few lines for plotting. And it gives you a wealth more information. I mean, I don't know how, if you did this by hand, I mean, I don't even know what you'd do. You just sort of guess, and you pick a point and see what it's like there, and pick a point and see what it's like there, and pick a point and see what it's like there. And just keep doing it until you narrow down, what your safe, where your safe operating zones are. But anyway, here's another example. In this case, looking at the required mud weight that will produce drilling-induced tensile fractures. So there's lots of ways, what you plot on here, you can decide, right, to give you the most information about the problem you're trying to solve. But the technique of using these is basically the same. You have to just go through all those transformations of equations and sweep through phi and delta. And that's what I'll ask you to do on your next homework, which I'll assign today and it'll be due Monday so that I can post the solution before test Wednesday. Right. And again, we'll give you enough opportunity to check all so just like on the previous exam, you'll have the opportunity to have checked out all your code to make sure it works on known solutions, so that when you solve a problem on the exam, you know you're using code that works. Okay, let's stop there today.